Hey there, ninth graders. Mr. Hamilton here today to give you some notes on Earth's energy budget day 2. So yesterday you learned a little bit about Earth's energy budget, and if you haven't watched those notes yet, I would highly encourage you to go back and view those notes first prior to doing these ones, because these ones are definitely going to build on some of the information that you should have learned yesterday in the day 1 notes. So our essential question for today is what happens to the energy that is absorbed by Earth? So that is what we're going to be looking at in more detail today, as we know that some energy is reflected by Earth and we know that some energy is absorbed by Earth. And so our question today is what happens to that energy that gets absorbed? And so we're going to first start with a little kind of review of some of the variables or the factors that affect Earth's energy budget. So some of those things have to do with where you are on Earth at any given point, whether you're near the poles of Earth or whether you're near the equator. Those are going to be things that are definitely going to have an impact on how much energy you get from the sun. And you saw that in the Sun-Earth modeling video that Ms. Viertz presented for you yesterday. There's reflection, which we call albedo, which you also learned a little bit about yesterday. That very much depends on the material type. It also depends on color, because what albedo measures is it measures the amount of sunlight or energy that is reflected back versus the amount that is absorbed. And so I'm actually going to show you right now just a quick simulation here, and this is something that I'll link on the page down below this notes video today. But there's this little simulation that kind of helps to understand a little bit of how albedo works. So in this simulator here, we have basically the sun over here, and we can adjust the brightness of the sun if we want it to be, 100% brightness, or maybe it's a really cloudy day and it's only 80, 50% or 60% or whatever. But we're going to stick with 100%. We'll just say that it's a nice, bright, sunny day. And then over here, you can actually choose the surface or the material that you want to find out a little bit about what percentage of the sunlight would be reflected as a result of that surface. So you can see here there's a bunch of different options. I can choose forest, grassland, oceans, fresh snow and ice, asphalt, clouds. There's a bunch of different options here. So I'm going to just pick a few of these and show you some examples here, but we'll start out with fresh snow and ice. So if we think about that type of material and the color of that, we're usually talking like bright white, right? So we know that surface is going to be really, really reflective. And so it's actually going to reflect about 85% of the sunlight that hits it, okay? Meaning that it's going to contribute to a significant drop in temperature because it's not going to absorb that heat. It's actually going to reflect it, okay? So you can see on the temperature scale over here, you can see that it would contribute to an approximate value of negative 148 degrees Fahrenheit if the whole Earth essentially was covered in snow and ice. Okay, if we go to something like asphalt, this is going to be the other extreme, right? So now we have something that's black in color. It's going to very much absorb that heat. This is why when we walk on asphalt in the summer with bare feet, it tends to burn our feet, right? We want to get off of it as soon as we can. So that's going to contribute to an increase in temperature of about 32 degrees. So based on the surface, based on the color, those things can increase or decrease albedo, which is just simply how much of the sunlight actually gets reflected back versus absorbed, okay? Because we know that absorbed energy causes things to warm up, all right? So that was just a quick kind of simulation there to show you a little bit more about albedo, right? Other variables that affect Earth's energy budget, we have things like clouds, which also can affect the albedo. The atmosphere, we're going to talk a little bit more about the atmosphere today, and then we have this idea of absorption and re-radiation, which we're also going to get into more detail here in just a moment, okay? Feel free to pause this video as I'm going along. If I go too quickly or whatever, feel free to pause and write down whatever you need to, okay? All right, so yesterday in the notes, you drew this diagram in your notes, or Ms. Viertz asked you to do that. So hopefully you did that. If you didn't, go ahead and draw it in there right now. You might need to pause this video in order to catch up. But basically, you've got the sun over here. We've got the Earth over here. You should have drawn the lines for the incoming sunlight, okay? And our input energy is coming from the sun, right? So when we talk about a budget, we always talk about input and output. Our input here is the sunlight or the energy coming from the sun. You might want to add this little parentheses to your diagram that says shortwave, because that's going to be an important thing to understand as we move through the notes today. So short waves is sunlight, and we'll talk about long waves in just a moment here. But this is, your drawing should look like this now. So you're going to want to add this output. You can leave the question mark out of there because we're going to fill that in today. But just write the word output. And then if you want to put these arrows in, these blue arrows for the output energy, that's what we're really going to focus on today, is we're going to focus on the output energy. Because yesterday you focused mostly on the input. Okay? So we know that energy moves in three different ways, through three different processes called conduction, convection, and radiation. So conduction is the way that heat or thermal energy moves through an object. So you can see that, this conduction here, this guy's hand obviously is going to be in danger in just a few moments as the heat from the fire moves up this metal stick that he's holding in his hand, right? So that's conduction. Heat can move through a material and travel through that material. Okay, and then we've got convection. Convection is how heat moves through liquids and gases, where it actually rises and then cools and then falls again. We get what we call convection currents, which you may have heard of. Possibly in 8th grade when you studied tectonic plates. And then we have radiation over here, which is basically just the idea that heat can move through or can travel through empty space, basically, can move towards something. Okay? So those three ways in which energy can kind of move either through a material, through a liquid or gas, or from one place to another. That's really what radiation focuses on, is moving from one place to another. Okay? So all objects emit radiation or heat. Radiation can be seen in what we call infrared images. This is an example of one right here, where you can see that the more yellowish areas, the bright yellow areas, are the areas that are radiating more heat. So the mouth and the eyes and the ears of this looks to be a wolf or something of that kind. That's radiating heat. So if we did this picture on a human, you'd have probably similar results. Your mouth, your nose, your eyes, those kind of things would be the things that are radiating the most heat out from your body. Okay, so all objects emit some form of radiation or heat. Okay, so when we get into a little bit more detail here, we know that absorbed energy causes an increase in temperature. So when we talk about the sun, beating down on the earth absorbs some of that sunlight energy, right? Which causes the earth to increase its temperature. The earth actually warms up as a result of that energy from the sun, okay? All objects emit radiation or heat, like we just talked about on the last slide, right? So hotter objects, things like the sun, emit shorter wavelengths of energy, okay, of heat energy, right? Cooler objects, like the Earth, for instance, which we'll get into in just a moment, are going to emit longer wavelengths. Okay, now this is important because we're going to talk in a little bit about certain gases in our atmosphere that absorb or do not absorb short or long wavelengths. Okay, so all objects emit heat. Hotter objects emit short wavelengths. Cooler objects emit longer wavelengths. Okay. So what this means is that the Earth, because the Earth absorbs heat from the sun, the Earth then re-radiates that heat back out, right? Because it absorbs the heat and becomes an object that is hot, it then re-radiates that heat back towards space, okay? But because Earth is a much cooler object than the sun, obviously the Earth doesn't produce as much energy or anything like that close to what the sun does. The Earth is a much cooler object than the sun. So because the sun is really, really hot and the Earth is much cooler, the Earth is going to re-radiate long wavelengths of heat energy, whereas the sun radiates short wavelengths because it's hotter. So back to the previous slide where we said that hot objects produce short wavelengths and cooler objects produce long wavelengths. The Earth in this instance is the cooler object. The sun in this instance is the hotter object, obviously. Okay, so as the sun heats up the Earth then re-radiates some of that energy back into space in the form of a long wavelength rather than a short wavelength. Okay. All right, so then if you go back to your drawing here that you should have down in your notes, you can add some things here. Okay, the output energy of the Earth, if we're talking about input and output, because we're talking about a budget, right? You've got incoming and outgoing, just like a money budget in the bank. You have incoming money and outgoing money, okay? The output in this instance is going to be the absorbed and re-radiated energy. Okay, so it's energy that came from the sun originally. It was absorbed by Earth, and then Earth heated up and re-radiated that energy back out towards space, towards our atmosphere and space. Okay, so that's the output energy, right? Now you also notice in parentheses here we have the long wave. Okay, that's important, right? Because long waves come from cooler objects, short waves come from hotter objects, right? So we've got our short wave coming from the sun, we've got our long wave coming from the Earth. So we're still kind of missing one variable here in our energy budget, okay? And that one variable that we haven't really talked about yet is this small part of the atmosphere that's made up of what we call heat-trapping gases, okay? And usually the word we use to describe them, which you might have heard about before, is called greenhouse gases, okay? These gases are super important because they absorb long-wave radiation, but they do not absorb short-wave radiation, okay? So this is where the short and the long comes into play here, because these gases will only absorb long-wave radiation, which we know long-wave radiation comes from the Earth, not from the sun, okay? And so these greenhouse gases are really important because what they do is they essentially trap some of that re-radiated energy from the Earth. They trap it in the atmosphere, and that radiation is then used to warm our planet, basically. That the atmosphere kind of acts like a blanket over our planet, and those gases, those greenhouse gases, are what trap some of that heat and keep it in, which is why we have mild temperatures on Earth. If those gases were, or if that radiation was allowed to just go back into space, then we would be not able to maintain the temperatures that we currently have on Earth. Okay, so this is just a picture to kind of explain that a little bit more. So we've got the shortwave radiation coming from the sun, and it hits the Earth. The Earth absorbs some of that energy, and then these smaller arrows, these lighter yellow ones, are coming back out, and you'll notice that some of the energy makes it all the way out, makes it back into space, but some of it is trapped in by the greenhouse gases, and that's what warms our planet, okay? So not all gases have the same behavior. Only some of these are greenhouse gases. So it's only really a small portion, about 1% of our atmosphere, that's made up of greenhouse gases, but that 1% is super important. Without it, we would have really, really cold temperatures on Earth. We'd all freeze up. We wouldn't be able to be supporting life on this planet without this small percentage of our atmosphere. So most of the gases in the atmosphere do not absorb long wave radiation, but these greenhouse gases do, and they serve a really, really important role for keeping our planet at mild temperatures. All right, this is kind of a summary of things, and I'm not going to spend a ton of time on this just to keep the video a little bit shorter here, but basically over here you have incoming radiation, over here you have outgoing radiation. So this is energy coming from the sun, this would be energy coming from the Earth, and there's a variety of different ways here. You can certainly pause the video and take a look at some of the different ways that energy comes in, as well as the ways that energy goes out of the Earth. All right, so lastly, the thing you need to add here is that there's heat trapped by greenhouse gases. So that's the last label to put on this diagram. We know that that's important because that helps to warm our planet, okay? So only a little over half of the absorbed energy is re-radiated by the Earth. What happens to the other energy? Well, where does it go? So because re-radiated energy goes back out from the Earth, what happens to the rest of it? Well, it just simply remains in the Earth. It remains absorbed by the surface of the Earth and actually helps to cause more of that change in temperature to keep our temperatures more mild. So the question becomes then, what if there wasn't an atmosphere? And you'll have to stay tuned to find out the answer to that question. So that wraps up our notes for today. Thanks for watching, and I will see you in another video at some point, I'm sure. So thanks.